Hello, welcome to Econometrics Melody. In this video, we will discuss about the variance of linear combination of random variables. So let us begin with the distributive property of the covariance. And we have four random variables wx, y, and z, and we want to calculate the covariance of w plus x with y plus z, and we get this expression on our right hand side, and this is equivalent to the cross product of wx with yz and summing the covariance of the pair of variables attained from the cross product of these variables. So drawing from this above expression, now let us see how to calculate the covariance of a plus b with itself a plus b, and this is equivalent to calculating the variance of a plus b. Again, if we take the cross product of ab with ab, then we get these four pairs of the variables and we calculate the covariance and we sum them all. The covariance of a is equivalent to variance of a, covariance of ab and covariance of ba, they are symmetric, so it is equivalent to covariance of ab, and covariance of bb, this is equal to the variance of b. Therefore the variance of a plus b is equal to variance of a plus twice covariance of ab plus variance of b. Now from this relationship, what happens if we want to calculate the variance of a minus b? Then it is very straightforward. If a and b are independent, then the covariance of the independent variables, that is 0. If this is 0, then we are simply left with variance of a plus variance b. So this is true for variance of a plus b as well. Now let us calculate the same for three random variables. So this is equivalent to the variance of a plus variance of b and variance of c plus twice the covariance of possible pairs. And again, if the variables they are independent, then in that case the covariance is going to be equal to 0. So we are left with. Now let us consider the case of a matrix. So how do we calculate the variance when we have a matrix? Let us say matrix X, it contains variables x1, x2, x3, x4, and so on. So how do we calculate the variance of X? So in a matrix, once we calculate the variance, we get the information on variance as well as the covariance. So this is equal to x transpose m0 x, and we divide by, and where m0, this is our deviation from mean matrix, it is an idempotent matrix, and we calculate it by using this relationship where I is our identity matrix, and this is small I, it contains one edge observations of the order n into. We have already discussed about this topic in our earlier videos. Now let us calculate the variance of linear combination of random variables, and we will express it in matrix or the matrix formula. So let us write the formula in general notation, then after we'll convert it into matrix notation. So we have a variable x, we divide by a, and we sum it with the variable y after scaling by b. How do we calculate the variance of this expression? This is equal to variance of ax is equal to a square variance of x. Covariance is proportional to the product of scales of the variables plus here we have a square variance of y. Let us try to express this in matrix notation. So it is a square variance x slash ab covariance of x y, and plus again ab covariance of yx following the symmetry of the covariance, plus b square and then variance of y. If we arrange it in matrix notation, a, b, first of all the scale or the constants, then after the variance covariance matrix of variable x and y, followed by a, b in vector form. This is the matrix representation of the above expression, and we have one linear combination of the variables x and y. So the general notation of the above, we have represented it in terms of matrix notation. But in case of matrix, we can calculate several sets of linear combinations by making simple adjustment in this notation or in this relationship. So let us say if we want to calculate dx plus and then another set of linear combinations x plus fy and so on. We need to make simple adjustment in this relationship. Simply add the scaling part. So this is the beauty of matrix. We can work in big data using matrix notation. This will be very efficient. Now let us see. We have here three sets of linear combinations. We want to calculate the variance at a single go. Now let us segregate the three linear combinations into matrix of scales of variables and the vector of variables. This is equal to variance of. Now let us represent the matrix of scales by A and the vector of variables by Z. Then we get that variance of AZ is equals to A variance of Z into A transpose. Therefore, variance of AZ is equal to A variance of Z into A transpose, where Z is equal to the vector of random variables x and y. Therefore, the variance of the linear combinations represented by BK is equals to B variance of K into B transpose. Here both AZ and BK, they represent linear combinations of the random variables. Some important points to remember. So variance of AX, and based on the nature of this X, we are going to use different formula. So if X is the vector of observations only, so let us say only the observations, then in that case, so let us say y is equals to ax, then in that case we calculate the variance of y making use of this formula y transpose m0 y, where our m0 is the deviation from mean matrix and I is our identity matrix, and small I is the vector n into 1 vector of ones containing ones as an element. And in general, the identity matrix is of order n into n, where n is equals to the number of observations, and we divide it by n minus 1, where n is equals to I transpose I. And if we substitute the value of y as ax, then we get. Now if we apply the property that A B transpose is equals to B transpose A transpose, then the final expression that we're going to get is X transpose A transpose M0 AX divided by I transpose I minus 1. We use this formula when X is simply a vector, that is, it contains n observations. Here AX represents the linear combination of observations. So in this case, we calculate the variance of X using expectation of X minus mu X transpose into X minus mu X. Once again, X is a vector of observations. Now let us see the case when X represents the vector of the variables, meaning thereby the elements of that vector is not the observation but the variables, random variables. In such case, we calculate the variance of AX is A variance of X into A transpose, and AX here is the linear combination of random variables, and in this case the variance of vector X with random variables is its elements is given by expectation of X minus mu X into X minus mu X transpose, which gives us the variance covariance matrix. And let me write the formula when X is simply a variable or a vector of observations only. To use this formula, vector X is the collection of random variables, let's say y and z, and in the latter case variable X, it contains n observations, numerical observations. Now let us quickly summarize these two conditions or properties. Now, before we wrap up, we will see this relationship, variance of linear combinations of the random variables. This is equal to A into variance of X into A transpose. We will see this by the help of an example in this data. We are considering 12 observations and our data container is ready for it, and we are going to create two random variables x1 and x2, and we are converting this x1 and x2 as matrix X. Let us create other useful matrix and vectors. Here capital I is the identity matrix, and this is small I that contains one column vector of ones, and this n is our sample size, and m0 is the deviation from mean matrix, which is equal to capital I minus I transpose divided by I transpose I. And we are considering only three sets of linear combinations, And the first set, it scales the variable x1 by 2 and the variable x2 by 3. And the second set, it scales the variable x1 by 3 and the variable x2 by 7. And the third set, it scales the variable x1 by 9 and x2 by 13. So matrix A contains the scales of variable x1 and x2. Now let us create matrix Y with the set of linear combinations is described by matrix A. So the first state, it scales x by 2, x1 by 2 and x2 by 3, and let us check. So 1 multiplied by 2 is 2 plus 0 is 2. We get this result over here. And let us check this one. So the first observation, we scale it by 9. 9 into 1 is 9. And the second observation, we scale it by 13. So this is 9. So we have three different sets of linear combinations of the variable x1 and x2. Now, first of all, we are going to calculate the variance of matrix X, meaning thereby we'll calculate the variance and covariance matrix that constitutes the variance of X1 and X2 as well as their covariance. And let us see what duplicate. This is our formula. So this is equals to X transpose M0X, and we divide it by the sample size n minus 1. So this is our general way of calculating the variance of matrix X. Let us see if we get this result, and we use the stata command to check whether we got the same result or not. And they are one and the same. Now is our matrix Y. This is the linear combinations of the variables x1 and x2. So three different linear combinations. So let us calculate its variance. So variance of Y using the general formula. This is again equal to Y transpose M0Y, and we divide it by the sample size and we get this result. Now we'll use the formula to calculate the variance of AX. So that is equals to A variance of X A transpose. We want to check whether we get the same result or not. Let us see it. So the first one, the variance, we calculated using the general formula, and the second one, we use the formula of variance of AX is A variance of X A transpose, and if we compare them, we get the same result. So they are one and the same. So this is it for this tutorial. Thank you very much for your time. Thank you very much, Econometrics Melody.